Evening, Dr. Baker. This is Ruben Pinkson with the Multi-Pactor Project, and I'm on Presentation 3 right now. Project mentors haven't changed from previous weeks. There's still Luke Sylvester as the grad liaison, and Ravi Joshi as our professor. For the project statement, this also hasn't changed. Our goal is still to simulate the multi-pactor effect that multiplies electrons in satellites that are located in outer space, and we'll do so by first learning more about the multi-pactor effect and secondary electron yield, SEY curves, by implementing new or already made curves with CST and electromagnetic field simulation software. And on that, I did find the acronym for CST was actually computer simulation technology, even if the thing was technically a design suite in its own name and didn't actually tell me what the acronym meant. Thirdly, we'll be simulating the multi-pactor effect of created curves in Spark 3D and analyzing the effects. And lastly, comparing simulation results with existing predictions. For last week's deliverables, I finalized the MATLAB simulations I was working on that demonstrated the interaction of an electron between two parallel charged plates and under the influence of a sinusoidal electric field. So this is a lot closer to what we're actually going to be working with in the project, since electric fields aren't always constant. I also created a computer simulation technology, CST plane wave simulation, that simulated a half wave, which was what my mentor recommended. There was more play around, but I'll get more into that later. And I uploaded the CST half wave into Spark 3D and performed visual analysis. Lastly, before I move on into what I'll be covering for deliverables, I did talk with my supervisor on what was the type of surfaces or materials we'd be dealing with, and we aren't going to be dealing with plastics. We'll actually be under the assumption that the multi-pactor occurs under a metallic surface that doesn't build up charge. So that's my answer to that question you had last week. But back to deliverables. For the MATLAB simulation of this week, it was an electron in a sinusoidal electric field. I did this under the assumption that it was under very similar circumstances, going between parallel plates yet again, separated by 1 centimeters, and having a potential difference of 10,000 volts. However, for this one, the equations were a little bit more difficult due to there being an extra factor of the sinusoidal electric field, which is why I found the derivatives of the electric field equation in order to derive velocity and distance for it. Below you can see some of the stuff I wrote on the blackboard, showing that idea of the first derivative getting the velocity and the second derivative of that getting distance. And the equation can be seen with A equaling to E naught, the amplitude of the electric field, times sine, with, of course, the angular frequency times time minus p for phase, and multiplied by the charge of the electron over the mass of the electron. These are the graphs I was able to generate from that. The one on the left, while not being very nice because it shows stuff after 1 centimeter, even though it's not supposed to, analytically shows that the electron is going to be continually making gains and losing distance, even if doing so after 1 centimeter according to this. But I like the one on the right a lot more, because it compares velocity to E field over time. So what this shows is that the electron's velocity is actually dependent on if it is in phase and going with the electric field. So at the start of this, it may not be exactly in phase or going with the in phase with the field yet, which is why that gain it makes isn't exactly up to its max. But the minute it gets fully in phase and with that electric field, it reaches its max velocity, and after it goes sorry, let me rephrase that. And after it reaches this peak, when the electric field changes direction at half of the wavelength, it goes all the way back to what it was before, because now it is working with the exact same magnitude in the opposite direction, causing it to go all the way back down and simply repeat the process over and over. This is again demonstrated in the energy versus position graph, where it's not even reaching the 10,000 eV because it starts off going in phase with the electric field up to about a little over 5,000 eV, and when the electric field changes direction, the electron's work is undone by going in the opposite direction, because it is doing so in the exact same magnitude, making simply repeat this process over and over again, showing the differences between a sinusoidal electric field and a constant one when dealing with an electron between two charged plates. For CST half-wave simulations, I messed around with CST a lot in order to manipulate height and frequency, making a lot of plane waves that weren't exactly desirable, but it's simply me getting my feet wet since I haven't worked with the software before. And from this, I was able to create a more desirable simulation that we could actually work with, which was just a half wave, and CST going through a simple vacuum. So compared to last week, it's no longer going through a vacuum, some sort of surface with a certain dielectric constant and then another vacuum. It's simply a plane wave going through a single vacuum. And this, of course, was set to a frequency of 1 gigahertz. And when this was imported into Spark 3D, I was able to do some visual analysis with the plane wave going through the vacuum. And I very much apologize for not being able to go deeper into what these mean, only because I was actually going to talk with my graduate student that I'm working with, Luke, last Friday, but the freeze occurred, so we weren't able to meet on that. And from that, I just more played around with Spark 3D and didn't exactly gain those explanations I would have wanted to what's occurring. The one on the left simply shows the magnitude of the electric field in the surface, ranging from about 5.7 times 10 to the 2, all the way up to 5.92 times 10 to the 2 in magnitude, of course in volts per meter for units. The right shows the magnitude of the magnetic field in the surface. This is a lot more spottier than the other one, and ranges from about 1.53 to 1.553. So these two aren't exactly showing a humongous difference, I believe, in the magnitudes from lowest to highest. Next, I tried working with the slice function, so the left simply shows what happens when I took a slice of the entire thing and put it out there. I really can't explain this because for some reason another rectangle appeared, but I was going to see if I could find out what that meant later on. And on the right, this is to me a lot more desirable. When I used the multi-pactor tool that is in Spark 3D, it was able to show about a 15-second video of the movement of electrons. My apologies for not having the actual thing recorded, but this is great because now I'm able to, as you can see from the little dots, we're actually in the state where we can start simulating the multi-pactor effect in Spark 3D, making really good time when it comes to working with the softwares. As you can see from the bottom right, this is occurring in the span of, at this time point, 4.7 nanoseconds, so it's still going really fast, even if it's not reaching the speed of light. So for next week's deliverables, I'll be working, of course, on getting more workable and desirable plane wave simulations in CST, and I'll be working on getting some more understanding of Spark 3D and being able to better explain and perform useful simulations. As you can see, the budget hasn't changed. Overall budget simply has increased in hours for myself, with a few more being added for the lab assistant, so we're still under budget. And the Gantt chart shows that we're still really nicely on track and getting even more ahead of schedule since I'm actually able to import things from CST to Spark 3D right now and perform analysis, even if it isn't complete. So we're still trekking along and it's going great. If you have any questions, please just send me them over the week, and thank you for your time.